Okay, so in this video, I will explain what the center of mass is, and this is a concept that we need to cover because we don't have now only point particles in our system. We have some number of point particles, and the concept of center of mass is required to understand this motion of a hypothetical point for the system which we call center of mass. Let me start with the one-dimensional case in 1D. So, I mean, in fact, you know what center of mass is in real life by instinct. Suppose you have a rod like this, is a one-dimensional rod, which has some length L and a total mass M. And supposing that this is a uniform rod, what we mean by uniform rod is every part of the rod is having the same density of mass and the same thickness anyway. So if you're asking that what is this center of mass for that rod, by instinct you will call that it's the midpoint, right? It's the midpoint. It is the center of mass for this rod. So it's a one-dimensional object, and for one-dimensional objects, uniform objects like this, center of mass is just the midpoint, the geometrical center for the objects. So what does this mean? I mean, why do we care about the center of mass? Well, if you just think about throwing this rod up in the air, like doing this projectile motion, okay? So suppose at some point, and this is the ground, you just throw this rod by, handing from one end, you throw it, okay? So it will go, supposing that it will go on a projectile motion. But the thing is, this is not a point object. If you had thrown at a point object like a stone, you know what the trajectory is, which trajectory should be like a parabola like this. But when you throw this by just grabbing from one end, what you observe that while going up in the air, this rod will do these funny rotations, okay, because it's an extended object, okay. So when you just concentrate on, let's say, one of the endpoints, let's say this point, the motion of this point, and trace it on the air. When you trace it on the air, the trajectory will look like maybe this, okay? It will go like a funny curve like this. Because, while going up in the air, the rod is rotating. So it's rotating. So that's what it looks like, okay? But when you look at only the center of mass, the point, a special point, that the center of mass of this rod, that special point, the center of mass, will go in a perfect parabola, okay? It is as if all the mass is just concentrated on a single point, which location on which we call center of mass. So that's the beauty of the center of mass. If you look at any point on the object, extended object, like throwing it like in a projectile motion, the trace will be very complicated. But if you just look at the special point, special location, which is the center of mass, that will go in a trajectory just like a point particle, and as if all the mass of the object, this rod, is concentrated on a single particle. This is the meaning of center of mass for very basic understanding. Okay, so this is what it sounds in for extended objects, but of course not all extended objects like in the regular shape. Like there are extended objects like in irregular shapes, and this can be like a planar kind of object, and in that case, how are you going to find the center of mass? Well, there are some methods to find the center of mass. One thing is that just take 2 points and hang this object on this first point, and another point is like let's say this point. Hang on another point on the second point. So on the first point, you just draw a vertical line. On the second point, suppose that this vertical line goes like this, and on the second one you hang on the second point. Again, draw a vertical line. So these two lines will cross at some point, and this locates the center of mass. It's very easy, in fact, to find the center of mass. Just read your textbook. It also mentions about this. For an irregular shape of objects, it's easy by help of gravity. It's easy to find the center of mass by hanging the object from 2 points. And the first point, you just draw a vertical line, and again in the second point, draw a vertical line. Just look at the intersection of these two lines. That intersection is going to be center of mass of that object. Again, if you throw this object, for example, this is an extended object up in the air, this will, go in a funny way, that rotating, and every point will trace some funny curve. But when you just concentrate on the center of mass, that point will just go in a trajectory which is a parabola. Okay, so this is it. I mean, for about the extended objects. But let me now try to find the center of mass of system of particles. System of, you have some point particles, more than one, 2, 3, 4, etc., n particles. So you are interested to find the center of mass for that system. Okay, center of mass of system of particles. So I will just concentrate on finding the center of mass location. Suppose you have one particle, with mass m1, and another particle with mass m2. There might be more than two particles, but I will just keep it simple. And what I write over here can be simply generalized into particles which are more than two particles, 3, 4, etc. So if these two masses are located one over here and over here, let's put these masses on a x-axis. Let's put this as 0, and this is x-axis. So if you know the location of mass 1, let's call that x1, and also location of mass 2, x2, then the center of mass for this system, well, by again instinct, you would say that, well, center of mass is going to be somewhere between these locations, x1 and x2, obviously. But to find it rigorously, this is the expression for it. Center of mass is somewhere here, let's say. If m2 is larger than m1, center of mass is going to be closer to m2. If m1 is larger than m2, center of mass is going to be closer to m1. So suppose this is the center of mass location. This is not a real particle, but it's just a hypothetical point, okay? So x center of mass, the center of mass location is just found by using this m1 times x1 plus m2 times x2, sorry, m2 x2, and divide this by the total mass, m1 plus m2. So if you have more than two particles, let's say m particles, x center of mass is going to be m1 x1 plus until mn xn, whatever the total number of particles. So this is going to be the sum of all particles, m1 plus until mn. Okay, this is the generalization. Okay, so for two particles, this is the case, and as an example, let me put m1 is equal to 1 kilograms, m2 is equal to 2 kilograms, and x1 is 2 meters, and x2 is, let's say, 5 meters. So in that case, center of mass location is going to be just 1 times 2 plus 2 times 5 and divided by 1 plus 2. So it is 12 divided by 3, which is 4 centimeters. So this is going to be at 4 centimeters. If this is 2 meters, sorry, 4 meters. Sorry, excuse me. This is 4 meters. If this is 2 meters, if this is 5 meters, and M2 is 2 kilograms and M1 is 1 kilogram, the center of mass for this two system of particles is going to be at x is equal to 4 meters. This is the way you find. Well, this is not the only story about the center of mass. Well, supposing that the particles are just at rest, this is how you find the location of the center of mass. But what if the particles are moving? Let's say the particles are moving with constant velocity. So finding the center of mass velocity in that case is going to be interesting. Again, suppose this is your one-dimensional coordinate system and you have mass m1 which is going with some velocity v1, constant velocity. You have mass m2 and this is also going with constant velocity v2. So if they are moving with constant velocities, certainly there is center of mass of these two particles somewhere in between, and if they are moving, obviously the center of mass is also will be moving, right? And we claim that the center of mass also will move with a constant velocity. As long as these velocities are constant, the center of mass velocity is also be constant. And how are you going to find the center of mass velocity? Again, by using the similar expression with that of location of the center of mass. This time we are going to use velocities. m1 multiplied by v1 plus m2 multiplied by v2 divided by the total mass. Again, if you, let's say, for an example, m1 is 1 kilogram, m2 is 2 kilograms. Let's say take v1 is 3 meters per second and v2 is 6 meters per second. In that case, the center of mass is going to be 1 times 3 plus 2 times 6 divided by 1 plus 2, which is, this is 3, this is 12, 15 divided by 3, it's going to be 5 meters per second. So if these are the velocities of these two particles to the right, then the center of mass for this system of two particles will move to the right with 5 meters per second velocity. Okay. Now, speaking of which the center of mass velocity, I will claim to you now that the center of mass velocity for a system of particle, okay, does not change in a collision. So let's check this statement. And suppose, you know, you have two objects, mass is m1, m2, and they are approaching each other with velocities v1 and v2. At some point they collide. After the collision they will move. Obviously they will move in probably in different directions with different velocities. v1 prime, this is m1, and v2 prime, this is m2. Okay. So after the collision, these are the velocities prime, and before the collision, these are the velocities. Also, before the collision, we have the center of mass velocity. Okay, center of mass velocity. Let's call this center of mass velocity before the collision, and let's call this center of mass velocity after the collision with a prime. So what is the center of mass velocity before the collision? It is by just using this expression definition, m1 v1 plus m2 v2 divided by the total mass. Okay. And in the second case, let's put this as prime because this collision took place and new velocities are acquired by these two masses, m1 v1 prime plus m2 v2 prime divided by m1 plus m2. Just I follow the definition for the center of mass. So we claim that these two velocities, center of mass velocities, VCM and VCM prime, before and after the collision, is going to be the same. That does not change. Well, we know that after during the collision or for all collisions, the momentum is conserved. What does that mean is that conservation of momentum for this general one-dimensional collision m1 v1 plus m2 v2, the sum of all momenta before the collision must be equal to sum of all momenta after the collision, v1 prime m2 v2 prime, right? This is something we know from conservation of momentum. If these are equal to each other, look at the nominators for VCM and VCM prime. Well, VCM nominator is in fact nothing but the sum of momenta, right? m1 v1 plus m2 v2. And the denominator for the VCM prime is again sum of momenta after the collision, m1 v1 prime plus m2 v2 prime. But we know that these sums are equal to each other, so that means center of mass velocity is not going to change during any collision. So it is as if like this center of mass velocity is going in some direction in some velocity, and it is totally insensitive to collision. By just following the center of mass velocity, center of mass point velocity, by just looking at it, okay, you can never tell whether the collision happened or not because it doesn't change at all, okay. So this is another nice thing about the center of mass concept. At least we know in a collision that there is one physical quantity associated with the system which does not change at all, and it is completely insensitive to collisions. Now I want to show you another nice application of the center of mass concept in this system. That there is a boy over here in the video and a board, surfboard, like this. Boy is standing on one end of the surfboard initially, and what he will do is now he will walk along the board, okay. While walking along the board, initially they are at rest, okay. The board and the boy is just at rest. The boy just wants to walk on in this direction toward the other end of the board. And while walking along the board, you might imagine what happens to the board, okay? While the boy is walking to the right, because his feet is going to be pushing while walking into the right, the feet will be pushing the board to the left. You might imagine that the board will go in the opposite direction while the boy is going in the right direction, okay. So first let's see what happens by running the video. Okay, so just you have seen what happens is that when the boy is walking to the right, you can easily observe that the board is going to left, and then he's suddenly doing the reverse, and he's until here is walk and go back, while she's going in the left direction, the board is going on the right direction. So there is an explanation of this, of course. As I said that if you think this system of boy and the board, so our system is now has two particles, two objects, one is boy and the other is board, and you can always define the center of mass for this system. Obviously the board has the center of mass, its own center of mass, somewhere maybe midpoint of its extension, and the boy center of mass is just over here, and their center of mass is going to be between the boy and the midpoint of the board, somewhere over here, okay. I claim that while the boy is walking back and forth, that center of mass of the boy and the board does not change at all, okay. Because there is no any external force acting on the boy on the board, supposing that the board has no any friction with the water, because you know water surface is very low friction, So there is not going to be a force on the board. There is not going to be a force. There is no any force on the buoy in the horizontal direction, of course. I'm talking about the horizontal direction. So all the forces involved are the internal forces. What I mean by internal forces, the force of friction between the feet of the buoy and the board. That in fact is the cause that the board is going in opposite direction while the buoy is going in the forward direction. But I claim that, you know, the center of mass does not change at all. And think about it, okay? And center of mass does not change at all because there is no any external force acting on the buoy and the board. If there is no external force, all forces are internal, and internal forces cancel each other because while the buoy is applying a frictional force in the backward direction, and that same frictional force is going to be on the buoy in the forward direction, and these two forces cancel each other because of the Newton's third law. So there are forces acting on the systems between the parts of the system, buoy and the board, but these forces cancel each other, and there is no net force acting on the totality of the system of buoy and the board. So that means the center of mass location will not move at all. I mean, that is the reasoning when you think about it. Also, maybe it might be helpful for you to just check the textbook and read the relevant part in the textbook. When there is no external force acting on the system, well, there are forces acting on the part of the system like buoy and the board, because board is moving backward. That means there is some kind of force on the board. But when you think about the totality of the system, buoy and the board, these forces cancel each other. When the forces cancel each other, something associated with the system has no any force on it and it will not move at all. So that guarantees that the center of mass for the buoy and the board system does not change at all during this walking back and forth. Okay, so I will use this idea to solve a problem. Let me put the problem on the board first. Okay, this is the problem. Suppose you are on a robot. Robot is like kürek in Turkish. So you're on a robot which has, let's say, a total length of 2 meters. Okay, and you are initially sitting at the right end of the boat, right over here. This is the dock, this is the ground, and this is the water. Okay, and the robot is not tied to the dock, so it just stays there at rest initially. But suddenly you just wanted to change your location from this right end to the back end of the boat. So just you walk on the boat and you just sit down on the left hand, okay, on here. So as you have just seen in this buoy and the surfboard example I have showed you in the video, while the buoy is moving in one direction, the boat is moving in the opposite direction, just to preserve the center of mass location. So the boat will move, okay, in this direction because you already moved to the left, and the boat will move to the right. But what I claim is that in both cases, and I just proved in fact this claim, in both cases the center of mass for the system of you and the boat will be not changing. So let's talk about the center of mass. Let's the weight, let's M2 is your mass, and this weight your mass is like 80 kilograms, and supposing that the boat has a mass of 60 kilograms, let's call that boat also let's assume that the center of mass for the boat is just midway, and this is M1, which is 60 kilograms. M1 is the mass of the boat and M2 is the mass of you. and you are initially located at from the dock at x is equal to 2 meters. The center of mass for the boat is 1 meters because it's midway. And well, the center of mass of the boat and you is going to be somewhere between this point and this point, of course. Since your weight is larger, suppose this is the center of mass point. Okay, this is the center of mass point. Well, I claim that while you relocate yourself to this part, and to the left side, this center of mass location is going to be the same for both boat and you, okay? And center of mass location is not changing. And supposing that the boat moved to the right by a distance of x from the initial, measured from the initial position of the back end. And the question is, what is this x? What is how many meters from the dock that while you're relocating yourself to the left end, how long this distance will go in the right direction? I mean, back end. What is the distance between the back end of the road, left end of the road, and the dock? This is the question. Okay. So, so you see, both the center of mass for the boat and also your locations change in both cases, but claiming that the center of mass for the system does not change at all in two cases. And let's write down x center of mass in the first case, right? We know that boat is located at x is equal to 1 meters because its midpoint and total length of the boat is 2 meters and it's 60 meters. M1 x1, first let me write down the expression. M2 x2, M2 is u, M1 is boat, and divided by the sum. And well, keep this without writing the numbers, okay? In the second case, prime, let's put this prime because it is another case. In the second case, since you are just x meters away from, because all measurements are done from the dock, from this point, we must have some reference in our coordinate system. This is x direction, and we choose this point as the reference point 0. So now you are located at x, and your mass is m2, m2 multiplied by x. And now the boat is just moved to the right by a distance x. That means the boat center of mass, which was at 1 meter initially, now it is located at 1 plus x meters. So this is m1. X1 was in 1 meters over here, but since it's moved a distance x more, it is m1 multiplied by x plus x1. Over here, x1 is 1 and x2 is 2 meters, okay, in the first case. Now, since the boat has moved by a distance x, its center of mass is going to be x plus x1. x1 is 1 meters, okay? And divided by the total mass again. And I already proved that this center of mass will not change. X center of mass is equal to x center of mass prime. In both cases, this center of mass point will not change upon relocation of yourself. So this will get us to equating these two. Denominators are the same. M1 multiplied by x1 plus m2 x2, and well, let's put now the numbers, okay? Let me put the numbers now. M1 is 60 multiplied by x1 is 1 plus m2 is 80 multiplied by x2 is 2 meters is equal to m2 is 80 times x and plus m1 is 60 x plus x1 was 1. Okay. So we have, let's say this is 60, this is 2 times 8 is 160, and this is 80x plus 60x plus 60. So these 60s will just cancel out. On the right hand side we have 140x. On the left hand side we have 160. So x is going to be 160 divided by 140. Okay, meters. Well, let's do this calculation. So the calculation gives you 0.14 meters. So upon relocation of yourself from right end to the left end of the boat will move from the dock, away from the dock, by a distance of 1.14 meters.